Right, first and foremost, apologies. The title that you see up here may not be the title that you see on your pages, but we sent this title across as a submission, and the Hadoop Summit Committee felt we should use Hadoop interchangeably with big data over there. So we could not kind of deny their request, but at the same time, just letting you know that we're going to discuss a lot more outside of just the Hadoop paradigm as part of the reference architecture that we get to, all right? Now, a little bit about myself. I'm Nishant Thakur. I'm a technical product manager for the big data services at Microsoft. So I work on the HD Insight service as well as the data lake set of services as a whole. And I'm responsible for key customer deployments as well as making sure that our field and partners are enabled to go ahead and talk as well as solution upon these technologies. In my prior life, I was in the consulting services with Microsoft, so I was implementing these architectures firsthand for a set of Fortune 100 customers, if I may say so. All right, now diving right into the session, and I've got a very simple agenda. I've got 35 minutes to talk about it. I'm going to keep it short and simple over here. We're going to understand what is the problem for fraud detection. We'll dive deeper into what is the expected outcome as to like what do I need to make sure that these kind of things don't happen. And then we look at a reference architecture to go ahead and understand as to whether a particular reference architecture can meet our needs. And then I'll try to deep dive into individual components of that architecture to try and explain where they fit and what kind of purpose they serve in the architecture. And then at the same time discuss about the applicability to a wider range of problems. So let's kind of set the stage here by understanding what the problem is initially. So essentially the problem that we are looking at is many-folds, right? Fraud detection usually is associated to financial services world, although more and more now it's getting into the retail world as well as the rewards and recognitions world, and any other world where there is any kind of compensation happening, either monetary or point-based, etc. All right. Now there are a few things to consider over here. Fraud is not just about a transaction. This fraud could be a practice or a process that has been implemented as part of the financial services portfolio itself. So here you see like 4 kinds of things that financial institutions are more concerned about today. So of course, the first one being detection of fraud, like how early can I go detect it? How can I prevent it? How can I make sure that there is no theft around all the money that I'm kind of dealing with? And then there are other aspects as to whether we are losing customers. Now you would say, how is that related to transactions or frauds, etc.? But essentially there is a lot of evidence around the fact that employees within companies are trading with others to exchange customers in return for benefits for themselves. So you could see patterns within customer churn which could lead towards customer transaction or customer application fraud, etc. as well. And then again coming to the legal requirements and compliance and exposure in various areas, etc., and how are you playing around with all of those pieces, that also accrues in some form or the other to some kind of fraud within the system, all right? Now let's just go ahead and take a deeper look at how traditionally these institutions have evolved, right? So essentially in legacy systems, they would look at all the historical data. They would have transactions, they would commit transactions, they would go ahead and process those transactions either at the end of the day or potentially even sometimes at the end of the week. And then when they wouldn't see their books matching, they would see certain gaps and try to address those gaps and try to drill down further as to what happened and try to plug some holes over there. But by that time, if if this particular transaction has gone through, the fraud's already happened. There's no point crying over spilled milk. The most you can get is get the person or an entity who has committed that fraud to justice, like either punish them or get them arrested or whatever that is. But you're not going to go ahead and improve the experience that your customers had. You've lost the loyalty of your customers for life after that, right? Now, in the current systems, what they currently have is, okay, well, I have a mechanism where I can go ahead and process all of this data really quickly. So now I don't need to wait till the end of the day or for the end of the week to go ahead and determine what my fraudulent activity is. I can determine that in a span of minutes or hours and potentially go ahead and schematize a mechanism where I would go ahead and reverse transactions, etc. But again, that is also after the fact. How do you get to a state where before a fraud happens, you have an indicator towards that fraudulent activity and that you can go ahead and prevent that from happening in the first place, or at least go ahead and flag that off as a fraudulent activity so that you allow your customers to have a certain threshold beyond probabilistic statistics around that to determine whether they want to proceed further with the sale to accrue to their revenue, or do they want to have a low risk profile and prevent those from happening in the first place, right? Now that's where we were. Again, opportunities for financial analytics really arises from a lot of things. So we discussed some of these in the previous slide as well. It's personalization of offers and banking experiences, like are certain customers getting preferential treatment or undue preferential treatment? Even that could be a reason for fraud. Of course, fraud detection in itself is definitely going to come in, and we'll discuss deeper, and that's the kind of focus of our discussion today. Again, customer churn prediction, prevention, as well as risk reductions and compliance, that's another very important aspect for financial analytics. Now, I show you this slide just to give you a glimpse of the kind of data that these institutions are dealing with. It is not just those transactions that are coming through. These institutions are maintaining a profile of a user with a 360-degree view on them, with their social profiles linked to it, with their banking profiles linked to it, with their wealth management profiles linked to it, with their investment profiles linked to it, as well as sometimes their professional profiles linked to all of this over here. Now, all of this accrues to a humongous amount of data to deal with. And traditionally, financial institutions have been very conservative towards moving into any of the new age technologies. So they've just been beefing up their servers on premises and adding more and more relational capacity into them. Of late, they've started expanding into some of this advanced analytics technologies, and they're trying to determine if there is a way for them to have a cheaper as well as more efficient solution for their problem, right? Now, let's just dive deeper into the fraud detection piece itself. So the first piece around that is definitely credit card fraud. Well, all of us have gone through it in some form or the other. I have gone through it multiple times. There are transactions that show up on my credit card which I have never purchased, and I have to literally go back to the bank, and there is a 3 months investigation process around this. And at some point the bank decides, okay, we'll take the hit on it and revert that transaction back. But they were not able to kind of go ahead and determine the root cause of the fraud, and they were not able to even kind of analyze as to how they could plug that gap for the future, right? Now, again, this could be just a single transaction, but determining why this particular transaction is a fraud could lead to another set of data sources altogether. So it could lead to where it happened. so geolocation. It could lead to where you are currently, so your travel profile. It could lead to what your professional needs are, so your professional profile. It could lead to what have you been talking about on social media, so it leads to your social profile. In addition to, of course, what is your underlying banking profile? Do you even go ahead and look at transactions of those values, or even have the appetite to go ahead and purchase some products like that? So all of that analysis needs to happen almost in real time. But in some ways, you're actually trying to determine some things beforehand such that you have a 360-degree view of a user or a customer before you even get to predicting or probabilistically determining whether this particular transaction is a fraud or not. The second piece around that is definitely money laundering. So lots of trades happening, lots of money exchanging hands. Is there any way that a particular transaction between two entities conforms to certain compliance, doesn't conform to certain compliance norms, and is actually a case of illegal trading over there, right? And the third one, of course, is e-banking fraud. So you got all of this transactions happening in your banking accounts, etc., and whether you can make any sense out of the patterns over there, or certain transactions are complete outliers and there is no reason for them to be there, etc., such that there is a very high chance of somebody losing money as a result of these. Okay? Now, coming back to the second point on the agenda, like we discussed all of those fraudulent activities. What is the expected outcome of a robust architecture if implemented correctly to detect fraud as well as determine reasons for them beforehand? So potentially, if I look at just these 5 points on our screen right now, it should suffice any kind of determination that you may need. So first one, of course, being, well, go ahead and determine if there is if the probability of this transaction being a fraud is above a certain threshold, and reject that transaction at the root. It may cause some kind of discomfort to the customer at that point in time if it is legitimate, but at least you can reason that through by giving them proper indicators and attributes as to why this particular transaction was rejected, right? The next one is definitely real-time alerts, and more banking institutions are getting into that. So you swipe a card, you get an alert on your mobile phone. Either you get to authenticate that transaction with a PIN, or you got to go ahead and authenticate that with a call to the banking institution itself. So you need to get all of these real-time alerts coming in so that you are informed of any activity that's happening either on your bank account or your credit cards or your financial profile as a whole. The third one is, of course, the real-time dashboards, like, okay, and this one's more for the institution. So you got managers sitting and observing your profiles, and they want information as to how certain patterns are being observed. There are analysts who are sitting and doing this day in and day out, trying to observe what kind of transactions are happening, and if any of this is happening outside of the realm of the probabilistic kind of acceptance levels. And that's where real-time dashboards comes in really, really handy. Okay? And the fourth one is, of course, in addition to just these alerting and real-time streaming options, you also need to go ahead and develop a learning of these transactions in real time, such that you can feed in these newer transactions as they are coming in to redefine the pattern of your expenditure or your organization's expenditure as a whole. And then, of course, the fifth one is kind of after the fact analysis. So it needs to have all kinds of audit trails and analytics implemented such that you can go ahead and dive deeper and determine what is required. So if you suffice all of these 5 criteria in a fraud detection or money laundering architecture, you've actually sufficed a lot of that in there, right? Now, What are the challenges there? And I'm sure everybody's gone through some form of this slide in at some point in time or other. So again, we discussed a lot of data sources, so that's a big data problem for sure. First thing is the volume, so it is definitely a very big volume problem that's coming through. The second is the velocity. Now, the number of transactions per second that are coming through for financial institutions, that's way above any relational or traditional system can manage. So, they definitely need to have a scale out architecture to first ingest and then process those streams of information as they are coming in. Third is the variety. Now, these financial institutions deal with a lot of other firms. So, each of them have their proprietary file formats. Some do XML, some do JSON, some do Avro, some do Parquet, some do some of the other file formats as well. And to be able to bring all of that inside the same paradigm and to be able to analyze that is way beyond what they've always planned for. And of course, when it comes to veracity, you need verified sources around any data that's coming through. So, the audit control pieces come in really handy over here, and data lineage becomes a necessity. Now, let's just look at what could be some of the architectural considerations as we start planning for such fraud detection application architectures. Now, the first one over there is of course the storage state. Well, what do you want that storage to reside in? Does it reside in a cache? Does it spill to a disk? Does it get to a distributed cache? Does it get to a distributed storage as a whole? Where do you want to store it, and what kind of querying mechanisms do you have around that? The second one being, okay, where do you want to store some of the data that is pretty static in nature and you're just appending more information every now and then, like the profile of the customer? Whether you store it directly into HDFS, do you get into a mechanism of edge-based clusters? Do you actually go ahead and prefer relational world to store this information, right? The third piece is potentially one of the most important in today's world, the ingestion framework. Now, in the financial world, it is not acceptable that even a single transaction gets dropped off as a result of a failure of one particular entity inside of your ingestion framework. So, you need to be very careful around what you are designing, why you are designing, and how you are designing that as well. Now, as you get into that, you have options like Kafka and Scoop and event hubs and IoT hubs, which are essentially messaging or buffering queues that are ingesting all of this data in humongous volumes and keeping it ready for you to stream across to an underlying stream processing system such that you can process them in the best way possible. And that's what leads us to the next point on the architectural considerations, the stream processing engines. Now, which of the stream processing engines are you going to go ahead and employ over here, depending on what kind of queries that you want to write for a fraud detection architecture, and which ones are going to support a scale out architecture in themselves such that you don't have to trade off in terms of the time required to process those streams as they are coming in real time. And then of course comes the analytics. Well, ideally speaking, this should be the first topic on this consideration, but in today's world, you look at that right towards the fag end, which may not be correct, and that's why this session, which is going to drive you through an architecture where it is implemented. So, whether you want to go ahead and do batch mode processing, you want interactive processing, you want to connect it back to BI tools, you want a report or a dashboard on top of it, and how are you updating all of this information and feeding it back to your learning systems such that they learn from it over a period of time and improve its accuracy on the detection algorithms, right? And then of course the last point over there, and last but not the least, and potentially the most important in this discussion over here, the machine learning. This is the place where you're actually detecting individual architectural components and you're showing up individual transactions and determining a probability or a score whether they are fraudulent transactions or not. So you need to have the most sophisticated algorithms implemented as part of your model such that your accuracy is way high. Now, with that said, I'm going to throw up a reference architecture up on the slide now, which we use very frequently as a base reference architecture for most of the fraud detection applications that we go ahead and create. Now, mind you, we've not captured everything over here. No one reference architecture can go ahead and do that, but we've tried to capture as much as possible from an end-to-end perspective. Now, let's just quickly walk through it and then we'll dive into individual components of it as well, right? So the first thing, of course, is the data sources. Well, you're getting trades and transactions, they are coming in real time. The second piece, which is very important for the financial world, is news, and they have various sources of news information coming through as well. Now, this is important, not because they would use these news items to go ahead and predict what's going to happen next, but more importantly, try and predict if somebody got these news items before they should have and they've used it to their advantage as well, right. So, there is a factor of fraud happening over there as well. And the third is, of course, all the user behavioral data. So, apps data from devices, their social profile, their banking profile, their financial profile, their professional profile, all of that's coming through as well. Now, some of it needs to get through a gateway and get into the ingestion framework or the gateway on the architecture side, but whereas some can connect directly to them. So, it is important while you're designing your architecture that you determine what gateways can accommodate what sources you want to connect back to, right. Now, once you've done that, then you get to the gateway, which is essentially your ingestion framework. This is the one point where all of your data is hitting in all of that velocity at any point in time. And today's global world, there's no 4 hours of downtime or 12 hours of non-working time for an institution. Every application is actually working 24/7. Even a minute of downtime leads to millions of dollars of kind of inactivity in the system, and that is not acceptable to any of those institutions. So, it is important that these ingestion frameworks have a very robust mechanism to ensure that each of your entities that are getting ingested are getting processed at least once, if not only once, okay. And you need to have checks in place if your architectural kind of consideration takes into place only the at least one ingestion framework, such that you don't duplicate transactions inside of your systems further on, right. Now, moving on to the third piece over there and starting right from the top. Now, the provisioning APIs, these are APIs that you would provision to go ahead and put in pull requests for your real-time dashboards and for your environments which need to show all of that information in absolute real time for dashboards to be observed by analysts or to be observed by banking tellers, etc. The second piece over there is potentially a relational store or a NoSQL store for all we care. That is actually storing all of your user profile. Now, in addition to the user profile, you're also storing some part of the user's recent activity, because a user is prone to show behaviors closer to his recent activity than activities that he would have done, say 5 years or 10 years before the date being observed over here. So, it's important to store both of those pieces in some form or the other, such that you can link it back to transactions or trades as they are happening in real time and conform to certain patterns within it. The next piece is, of course, stream processing. Now, this is another very important piece. Here is where you actually bring in those transactions perform some calculations and aggregations on top of it, try and compare it to some of the patterns from his behavior, as well as try and call certain APIs into the machine learning ecosystem to determine if the risk is too much for this transaction to go through. And mind you, this is actually connected back to your applications as well as connected into your data lake environment. Now, what does the data lake environment have to do over here? Well, the data lake is the place where we are storing, ultimately dumping all of these transactions in its native form, as well as keeping a store of the entire portfolio of data for this whole application. All of the other sources or applications or services or products are actually connecting into this data lake for some kind of determination of the right data, right? Now, that's where you need to make sure that the ingestion engine as well as the stream processing engines are capable to dump all of that data into your data lake as well. If that cannot happen, it would ideally mean that you have to go ahead and create a new mechanism altogether to go ahead and read data from your streams and then go ahead and dump it back into your data lake over here. Now, the next part is, and this time I am going to go bottoms up, is the analytics and the machine learning piece. The analytics and machine learning pieces is very important over here as well. In terms of scale out processing, because of the humongous amounts of data, in terms of the variety of data that we are dealing with, in terms of what kind of tools that we need to deal with all of this data, as well as to be able to perform at a range which is required for such institutions. And thus, the Hadoops and the Spark scale out architectures work really, really beneficially in this particular analytics environment over here. And once you've actually processed all of that data, you can then go all the way up to your app backend and source information out of this data and provide this to the dashboards and the reports that are actually consuming it. And of course, you're going to have custom applications and line of business applications and solutions, as well as connectors that are connecting back to either your analytics platforms or your stream processing engines or even your application backends thereof, right? Now, that's kind of a very robust reference architecture that could go ahead and suffice data as it comes in. Now, let's go ahead and take a look at what kind of products would you want to go ahead and add onto each of these layers as they come across. Now, a quick disclaimer here, I've talked about some of these products on this architecture. There are more. I've talked about some of them that I am most familiar with, and they cater to these layers the best way possible. But there are different flavors of the same products as well, and they would sit as well on those layers as these products. So, for example, for the ingestion gateway, you could go ahead and use Kafka, or you could go ahead and use things like the IoT hubs or the event hubs to ingest all of those events as they come in. For the stream processing engines, you got the capabilities of bringing in Storm or Stream Analytics, which is an Azure service which allows you to write simple SQL-like queries on top of streams as they come in. Or it could be Spark streaming if you're vested well into the Spark ecosystem. Onto the data lake side, you want to either go ahead and store it inside, and this is not an option. You need to bring in all of your native data in its native form, because today you don't even know what questions to ask of the data. Some research actually proves that today you're just making use of 5% of the data that you currently possess. And in the future, when you learn to ask the new questions of that data, you would actually want the data in its native form such that you can find patterns from it rather than curating it and processing it and losing certain attributes of it. And that's why it is important for you to store the data in a data lake in its native form. And the kind of products that you can use over here are potentially the Azure Data Lake or the blob store or the object stores that are available around it. Now again, when I say you got to go ahead and store it into an object store or a data lake store, that really does not mean that you're connecting all of your applications to that raw data all the time. You could actually spin up, let's say, a hedge-based cluster on top of that into your data lake and then connect your applications into that as well, right? And when it comes to the analytics and the machine learning pieces, of course, you got the capabilities of the Hadoop tools like Hive and Pig and all of those, the entire ecosystem around that, as well as Spark with Spark SQL and Spark machine learning libraries, etc. And then you've got third parties as well, like Microsoft has a machine learning service called Azure Machine Learning, which is very well integrated into this ecosystem such that it can consume data and make life much more easier for data scientists to create model and deploy and operationalize them, right? And then of course, the most important pieces like these financial institutions have hundreds if not thousands of models implemented in R. And you need to have a mechanism for them to be able to run these models on top of these scale out architectures as well. So for example, getting those R models and executing it on top of a Spark cluster or a Hadoop cluster to take benefits of their scale out architectures, which is very, very important. Again, for the profile storage, if you need a NoSQL store, it could be the document DB or it could be a SQL DB for all we care. What is it like? You're going to have 1 billion customers, potentially a very small subset of 1 billion customers, which can definitely be stored inside of a table in SQL Server and be queried in sub-second query response times given the right kind of priorities in there. And this data is pretty static in nature. So you are only updating this data on a basis when you process all of that humongous data that is coming into your data lake to find patterns using machine learning models on top of that, right? Now, let's just go ahead and show you a quick glimpse of this data. And I know I'm really running short on time, so I'm going to keep it really short over here. Now, here is an application that we have, which is actually simulating kind of a financial system that would implement. So just imagine having 40 years worth of trading data and you being able to determine things like the geographical exposure, the compliance, the performance of all of the data as it comes in, and you've got advisors in your organization. So you're being able to go ahead and calculate, okay, based on the portfolios that they manage, who are the better performers and who are not. Just imagine all of this data being streamed live as it's coming in, as well as news and videos being streamed across onto this environment. And then you being able to determine machine learning alerts coming across over there. And as we see, there is a suspicious trading alert that comes up on my page over there as well. Let's go ahead and see if I can click through that and see what's the data that's coming through. Now, this actually embeds a reporting, in fact, a real-time reporting environment onto my application. Hopefully it comes up. And what this is going to do is it's actually going to go ahead and plot analysis from machine learning models for me to reason through some of the data as it comes through on the dashboard. So I can go ahead and observe certain attributes of the transactions that have happened. I can see it from the perspective of a historical analysis, as well as bring that through onto my dashboard. Let me actually go ahead and open it up. Here you see that the suspicious trade dashboard coming up over here. So what are the kind of customers who are showing suspicious trades? What is the analysis? Why does it detect that it is a suspicious trade? Well, you see this particular customer over here, Michael Allen. Well, Michael Allen actually has been trading in the sub 10K limits. Suddenly, he started trading in the 30K limits, and these are just a few and far in between. Whereas you can actually observe that there is a bump in the price of the stock right after Michael Allen actually traded these. Now, to the naked eye, this might not be visible. But for a machine learning model that's working through and observing data and surfing through all of this data as it comes in, this is actually very, very observable. Now, determine working through a 10 terabyte data set to determine or analyze such patterns. Even in our model would take hours if not days to go ahead and process that. But with R, now you have the scale out capabilities on top of Spark and Hadoop clusters so that you can go ahead and process that in a span of minutes if not a couple of hours and get this determination coming through in almost real time to your applications and determine if these transactions are kind of legitimate or not. So while these transactions are coming in, you can actually fire up a REST API query to the data source and get information back from it to determine whether you want to legalize that and commit on it or not, right. Now, that is just one of the pieces, and let us just revert back to the presentation here and talk through the individual components. Now, I spoke through the ingestion framework, of course, a very, very important piece. It needs to be robust in a way such that it can support the ingestion of thousands if not millions of events a second, and you are able to stream it across to your complex event or stream processing engines and process the data in real time as it comes through. Now, what's important also over here is that it should support a lot of device sources, etc. So you need to bring through, not in full screen mode. So you need to bring through all of those devices data into the environment over here and potentially even go ahead and curate and process that data to enrich your user profile, right. Now, again, the user activity, you need to be able to plug in all the operational sources to it as well, because you want one version of the truth and you don't want separate subsystems which cannot talk to each other around this environment. The second piece, and we talked through this one at depth, is the stream processing. So essentially, these are the kind of activities that you would do from a stream processing engine as a whole. So you're going to go ahead and bring in all of your data. Now, each of these could go ahead and perform some kind of analysis like data aggregations or data enrichment, or they could just go ahead and make calls to machine learning models using REST API calls such that you get a determination of fraudulent probability right at the root of the transaction itself, and before you commit on that transaction you can send a notification to the consumer saying, okay, this is what's happening, go ahead and confirm or deny. We think there is a high probability of it being a fraudulent transaction. And then of course, it needs to go ahead and output all of that data as well for historical analysis, because that is part of the pattern. Has that account shown some kind of behaviors where a lot of fraudulent probabilities have been brought in, but still all of those have been legitimate, which means that the risk appetite for that particular customer or consumer is pretty high, right. And again, just a little deeper view around the stream processor examples and the processing that needs to happen using the stream processing pieces as well. Now, I want to surf through the rest of the slides, which are just another point of discussion of what we wanted to bring in, but this one is really, really important in terms of the high scale compute models. So you want to go ahead and bring in the reliable actors around that to go ahead and immerse your processing engines around this space, as well as you want to determine whether data needs to be processed in high compute environments or whether you really need these analytical processing engines to be in place over here. The most important piece, and probably something that I kept for the last, potentially the analytics architecture. So this is what you would want to go ahead and keep your analytics architecture looking like. So essentially, you're going to get near real-time events or other transactional events coming in, which would get into your stream processing engines. Now the stream processing engine is just a processing engine, so it does not understand any kind of metadata about your information. So it's going to go ahead and get some reference data from either a relational store or potentially a NoSQL store or the data lake directly. And then it's going to go start hitting your machine learning models for real-time scoring of these events as they are coming in. Further on, all of this streaming data as well as the batch data goes inside of the Azure Data Lake store. And then you use tools like, let's say, the Azure Data Lake Analytics or the uSQL language or the Hive and Pig languages or Spark SQL, etc., to go ahead and process that data as it comes in. And further on, you're using this data to go ahead and train your models as they're getting up as well, and you're reporting and dashboarding upon them. So that's pretty much the architecture that we wanted to talk about. Pretty much at the fag end of my presentation here, I'm going to go ahead and just keep it back onto the Q&A section for any particular questions that you may have around this. Of course, the slide deck is already published and available to you as it comes up. So thank you so much for spending time with me during this session, and I hope I could kind of share some insights into architectures that we've implemented. Thank you.